There is a star dying in plain sight, and it's not the one we have been watching. For decades, astronomers pointed at Betelgeuse and said, "That is your next supernova. That is the one. Watch it." And we did. We watched it dim. We watched it recover. We built entire research campaigns around it. Meanwhile, 90 light-years closer to Earth, there is another red supergiant. It is losing mass 10 times faster. It has a companion permanently ionizing its atmosphere. And it has never, not once, been given the same level of scrutiny. The star everyone ranked second might actually be first. Stay with me. Subscribe if you have not, because tonight I am going to show you exactly why what we chose to ignore might be the most important object in the sky. You have been watching the wrong star. That is not a metaphor, and it is not clickbait. It is, as best as current astrophysics can tell us, a genuine possibility, one that the scientific community has been quietly circling for years, while the rest of the world keeps its eyes locked on a red giant in Orion. Betelgeuse, the star everyone knows, the star that dimmed in 2019 and sent the internet into a brief, beautiful panic. The star that has a companion, a collapsing timeline, and enough dramatic presence to headline every next supernova article ever written. Betelgeuse is famous. Betelgeuse is watched. And Betelgeuse, it turns out, might not even be the most dangerous red supergiant in the sky right now. That title may belong to Antares. If you have heard of Antares at all, you probably know it as the bright reddish star anchoring the constellation Scorpius. You might know it's big. You might vaguely remember someone telling you that it's also a supernova candidate. What you almost certainly have not been told is that Antares sits roughly 550 light-years from Earth, while Betelgeuse sits at approximately 640. That difference, about 90 light-years, does not sound like much until you remember how light and energy behave across distance. The relationship is not linear. It follows what physicists call the inverse square law, which means that as distance doubles, brightness drops by a factor of 4. Antares, being closer, would appear approximately 0.3 magnitudes brighter than Betelgeuse at peak explosion brightness. That is not a rounding error. That is a real, measurable advantage, one that almost never comes up in popular discussion. But distance alone is not what makes this comparison so uncomfortable. The number that should be making astronomers more nervous is the mass loss rate. Antares sheds somewhere between 1 and 2 times 10 to the -6 solar masses per year. Betelgeuse, by comparison, loses somewhere between 1 and 3 times 10 to the -7 solar masses per year. Let me translate that out of scientific notation for a moment. Antares is losing mass at a rate roughly 10 times higher than Betelgeuse. 10 times. And mass loss is not a trivial data point. When a red supergiant starts shedding its outer layers at an accelerated rate, it is one of the clearest observable signals we have that the star is entering its most unstable evolutionary phase. The outer layers are losing pressure. The equilibrium that has kept the star from catastrophically collapsing is slowly eroding. The star is, in the most literal sense, falling apart. Then there is the companion. Antares has one, a hot B-type star designated Antares B, and unlike Betelgeuse's companion, which passes through the outer atmosphere periodically, Antares B is permanently embedded within the extended outer envelope of the supergiant. It is not a visitor, it is a resident. And that distinction, as we will get into, changes everything about how these two stars are actually behaving. You have a star already losing mass 10 times faster than the famous candidate, sitting closer to Earth, with a companion permanently agitating its atmosphere from the inside. And yet it is the second name on the list. It is the afterthought, the footnote. The star behaving more aggressively in every measurable way is not the one we are watching, and the deeper you compare them, the less confident that ranking becomes. Something changed after 2019. For most of modern astronomy, Betelgeuse was the easy answer. Ask any astrophysicist which nearby star was most likely to go supernova on a human-relevant timescale, and the answer came back quickly. Betelgeuse, probably within the next 100,000 years, give or take. That was the consensus. It was tidy. It was repeatable. Then, the Great Dimming happened, and that tidy consensus started developing cracks. Between October of 2019 and February of 2020, Betelgeuse faded to roughly 40% of its normal brightness. It was the dimmest the star had been in recorded modern observation. The internet collectively wondered if this was it, if we were watching the first signs of imminent collapse. It wasn't, at least not in any immediate sense. The current scientific explanation involves a combination of two factors: a temporary cooling of the star's surface, caused by a massive convective cell pushing material outward, and the formation of a dust cloud from expelled stellar material that briefly obscured part of the star from our view. What looked like a death rattle was actually closer to a particularly violent sneeze. But here is what changed in the aftermath of that event. Researchers began looking more carefully at Betelgeuse's binary system, and what they found disrupted the old models. There is a companion, sometimes informally called Siwarha in certain research discussions, with an orbital period of approximately 5.8 years. This companion does not orbit Betelgeuse from a safe distance. It periodically plunges through the outer atmospheric layers of the supergiant. And that interaction appears to be responsible for some of the star's most dramatic behavioral features, including events that strip outer mass and a mysterious long-term brightness variation with a period of around 2,100 days, known as the long secondary period. The companion is not a passive observer. It is an active disruptor. What this did to the timeline models is significant. The previously cited estimate of roughly 100,000 years was already a rough approximation, but the discovery of this companion interaction introduced a new layer of uncertainty. The models that produced that number were not fully accounting for episodic binary disruption. They were treating Betelgeuse as essentially a single star system moving through standard evolutionary stages. Once you factor in a companion that regularly disturbs the outer envelope, the certainty of that timeline does not necessarily shrink. It diffuses. It becomes a wide probability range rather than a reliable estimate. To be precise about what this means, no astronomer has a direct measurement of how much fuel remains in Betelgeuse's core. There is no instrument that can look through the outer layers and read the silicon or oxygen reserves. What we have are surface signals, brightness, temperature, spectral composition, that we feed into stellar evolution models that then produce estimates. Those models are good. They are not perfect. And the important shift that happened after 2019 is not that Betelgeuse is necessarily closer to exploding than we thought. It is that we are less certain about where it stands than we assumed. And here is what makes this relevant to the comparison with Antares. Antares has not gone through this kind of deep, focused reanalysis. Not yet. The gap in attention is not subtle, and it is not accidental. It is structural. After the Great Dimming, Betelgeuse became arguably the most watched star in the sky outside our solar system. Research campaigns multiplied. The Very Large Telescope's Sphere instrument imaged its surface in direct detail. The Atacama Large Millimeter Array captured millimeter wavelength observations of the surrounding envelope. The Hubble Space Telescope contributed ultraviolet spectroscopy. Papers accumulated. Citations built on citations. A rich, dense, interlocking body of literature developed around a single star, and that literature became its own gravitational force, pulling more research, more funding, and more attention toward it. Antares, in the meantime, has been observed. It is not unstudied, but it has not been subjected to this kind of unified, coordinated reanalysis campaign. There is no post-event forcing function that redirected the full weight of modern observational astronomy toward it, and some of that is simply practical. Antares sits near the galactic plane, meaning it occupies a region of sky crowded with background stars, gas clouds, and interfering signals. Isolating Antares cleanly against that background is harder than isolating Betelgeuse, which sits at a higher galactic latitude with a relatively uncluttered field of view. Observational difficulty is a real factor, but there is something else operating here too, and it is worth naming directly. Orion is one of the most culturally recognizable constellations on Earth. It is visible from nearly every inhabited latitude. It anchors the winter sky for a huge portion of the global population. Betelgeuse, as the bright red shoulder of Orion, benefits from this cultural prominence in ways that translate directly into scientific attention. Scorpius and Antares are more seasonal, more southern, and less embedded in global astronomical iconography. That should not affect how much attention a star receives from professional researchers. But the feedback loop of public interest, science communication, funding, and research momentum does not operate in a purely rational vacuum. Attention flows toward what is already being talked about. In science, this is sometimes called literature bias, the phenomenon where heavily studied objects attract more study, not necessarily because they are more important, but because the infrastructure of prior work makes new work easier to build. It is not a conspiracy. It is a structural feature of how research accumulates. But the consequence here is real. The absence of a deep reanalysis of Antares does not mean Antares has nothing to reveal. It may simply mean no one has looked as hard. And there is at least one measurement already in the data that, if you weight it appropriately, breaks the whole ranking. Mass loss is the number that changes the conversation. When a red supergiant sheds material into the surrounding space, it is not just leaking. It is releasing the outer envelope that provides the pressure counterbalancing the core's gravitational pull. Think of it as the structural tension in a bridge cable slowly fraying. The bridge can look perfectly intact on the outside, while the internal load-bearing structure deteriorates. A star losing its outer mass at an elevated rate is displaying, in the most direct observable way we have, that the equilibrium maintaining its existence is under strain. Antares loses somewhere between 1 and 2 times 10 to the -6 solar masses every year. Betelgeuse loses somewhere between 1 and 3 times 10 to the -7 solar masses every year. Those ranges overlap slightly in their extremes, but the central comparison is consistent across multiple independent studies. Antares is losing mass at a rate approximately 10 times higher than Betelgeuse. This is not a disputed finding. It is not a fringe measurement. It appears in the peer-reviewed literature. It is derived from multiple observational techniques, and it has been stable as an estimate even as other parameters around both stars have been revised. Now, a responsible narrator has to be precise here, because mass loss is not a simple variable countdown timer. The rate at which a red supergiant loses mass is influenced by several factors simultaneously. Rotation speed matters. Faster rotation can drive stronger stellar winds. Metallicity matters. The chemical composition of the star affects how radiation pressure couples to the outflowing material. Binary interaction matters enormously, as a close companion can gravitationally and radiatively accelerate mass loss, independent of the star's internal evolutionary state. So it is not correct to say that because Antares loses mass faster, it is automatically further along in its collapse sequence. The high mass loss rate could reflect binary influence from Antares B as much as it reflects the star's internal state. But here is the point that gets consistently underweighted in popular discussions of these two stars. Even accounting for all those confounding variables, mass loss remains one of the clearest observable indicators we have of advanced instability in a red supergiant. It is not sufficient on its own, but in a multi-factor comparison, when Antares wins on distance, wins on mass loss rate, and hosts a companion with a qualitatively different, and in some ways more continuous, mode of disruption, the confident ranking of Betelgeuse as the more imminent candidate starts to look less like settled science and more like a default assumption no one has seriously challenged. Are we prioritizing dramatic events over sustained indicators? That's worth asking, because the way these two stars are breaking down is not even the same process. Let us be precise about what is actually being claimed here and what is not. This is not a claim that Antares will definitely go supernova before Betelgeuse. No such claim is supportable with current data. Stellar evolution models cannot resolve which of two stars in similar late-stage conditions will reach core collapse first, particularly when the key information, the actual composition and state of the stellar core, is not directly observable from Earth. Anyone who tells you with confidence that either of these stars will or will not explode within a specific time frame is overstating the science. What is being claimed is more specific and, in some ways, more troubling. When you line up the measurable indicators, proximity to Earth, rate of mass loss, nature of binary interaction, geometry of outflowing material, Antares does not rank clearly below Betelgeuse. It ranks alongside it, and in several specific categories, it ranks above it. The confident, repeated, widely circulated claim that Betelgeuse is the nearby supernova candidate is not grounded in a comparative analysis of both stars. It is grounded in the cultural and observational history of Betelgeuse, which is not the same thing. The central tension here is this: we are trying to rank two stars by how close they are to an interior event. Core collapse, using only exterior signals. That is like trying to determine which of two old buildings is closer to structural failure by examining only the paint on the outside walls. The paint tells you something. It does not tell you everything. And when the building you have been watching closely looks more dramatic, while the one next door has been quietly losing its foundations, you may be looking at the wrong problem. What we know, both stars show measurable surface behavior consistent with advanced evolutionary stage. Both have binary companions that are actively disrupting their outer envelopes. Both sit within a range where, on a cosmic timescale, a supernova in our lifetime is not implausible. What we do not know: the exact stage of nuclear burning in either core, the remaining fuel reserves, the precise timeline to collapse. We are comparing incomplete signals from hidden interiors. And to understand why that comparison is so difficult and so important, you have to look at how each star is actually failing, because they are not dying the same way. Imagine a companion star as a moon circling a supergiant, except instead of raising modest ocean tides, it is gravitationally churning the outer layers of an object roughly 700 times the diameter of our Sun. That is roughly what is happening in both the Betelgeuse and Antares systems. But the nature of the disturbance is fundamentally different in each case, and that difference matters more than the popular comparison of these two stars usually acknowledges. Betelgeuse's companion, moving in that roughly 5.8-year orbit, periodically plunges through the outer atmospheric layers of the supergiant. The interaction is real and consequential. It strips material, triggers mass loss events, and has been linked to some of the long-period variability in the star's brightness. But it is episodic. The companion comes in, disturbs the envelope, and moves away. The disruption has a rhythm. It has gaps. In between orbital encounters, the outer layers of Betelgeuse have time to partially settle, redistribute, and re-establish something closer to equilibrium before the next encounter arrives. Antares B operates on a different principle entirely. Antares B is a hot, luminous star of spectral type B, meaning it emits strongly in the ultraviolet, and it sits at a separation of somewhere between 200 and 500 astronomical units from the primary star. That sounds like a comfortable distance until you consider that Antares itself has an outer envelope so enormous and extended that even at several hundred astronomical units, Antares B is effectively embedded within it. This companion is not a periodic visitor. It is a permanent resident of the outer atmosphere. The disruption, therefore, is not episodic. It is continuous. Antares B exerts gravitational influence on the envelope material around it constantly. It irradiates the surrounding gas with ultraviolet light constantly. There is no recovery period. There is no interval during which the outer envelope of Antares gets to redistribute and restabilize before the next disturbance arrives. The star is being continuously, persistently agitated from within its own outer layers. Whether continuous disruption produces more severe instability than episodic disruption is an open question in stellar astrophysics. The models for binary interaction in red supergiant systems are still being developed, and the specific case of a permanently embedded hot companion has not been fully characterized. But the conceptual distinction is real, and it suggests that the instability patterns of these two stars could be qualitatively different. Not just different in degree, but different in kind, and that continuous interaction leaves a visible fingerprint in the data. There is a glow around Antares that does not exist around Betelgeuse, and it is not decorative. The ultraviolet radiation from Antares B, that hot, embedded companion, ionizes the surrounding gas in the outer envelope of the primary star. Ionization means the radiation is energetic enough to strip electrons from atoms in the surrounding material, creating a charged plasma rather than a neutral gas. This ionized region is directly observable. It manifests as a circumstellar nebula around Antares, a faintly glowing envelope of energized gas that surrounds the primary star and extends outward into the surrounding space. You can observe it. It has been measured. It is one of the clearest pieces of direct observational evidence we have that Antares B is actively interacting with and altering the outer atmosphere of the supergiant. This is categorically different from what happens in the Betelgeuse system. The interaction there is primarily mechanical, gravitational. The companion moves through the outer layers, exerts tidal forces, strips material, and perturbs the gas dynamics of the envelope. It is a physical disruption, like a boat wake moving through water. The Antares system adds a second layer. The companion is also altering the gas through radiation. It is simultaneously pushing on the material gravitationally and energetically exciting it through ultraviolet bombardment. Ionization changes the behavior of the surrounding gas in ways that matter for how that gas moves and cools. Ionized gas has different opacity properties than neutral gas. It responds differently to pressure gradients. It radiates differently as it cools. If the outer envelope of Antares is being kept in a persistently ionized state by its companion, the dynamics of how mass is lost, which directions it flows, how efficiently it escapes the system, how it interacts with the surrounding interstellar medium, could be meaningfully altered. Does this bring Antares closer to collapse on a measurable timescale? That is the honest answer. We do not know. There is no confirmed causal link between the ionization of the outer envelope and the timing of core collapse. The core and the envelope are, in some sense, operating on different physics. But an actively disturbed, continuously ionized outer atmosphere is not a sign of a stable system. It is, as the astronomers who study it would likely agree, a sign of a star whose envelope dynamics are being persistently destabilized by an internal energy source. Antares is surrounded by a glowing, disturbed atmosphere, and that atmosphere is not settling down anytime soon. This is constant agitation, not periodic shocks, and that instability is not evenly distributed. There is a concept in stellar astrophysics that does not get enough attention in popular science discussions, and it is called asymmetric mass loss. The idea is straightforward once you hear it. A stable star should, in broad strokes, shed material more or less evenly in all directions. The stellar wind flows outward symmetrically. The envelope expands symmetrically. When you start to see material being preferentially ejected in certain directions. When the outflow has a geometry, a preferred axis, an uneven distribution, that is a signal that something has broken the spherical symmetry of the system. Antares shows this clearly. Infrared observations of the Antares system reveal a bow shock, a structure formed where the stellar wind slams into the surrounding interstellar medium at an oblique angle, indicating that the outflow is not uniform. The envelope is irregular. The material is not leaving the star in a smooth, symmetric sphere. It is being channeled and redirected. The geometry of the mass loss has a shape that reflects underlying asymmetries in the star's behavior. Betelgeuse also shows this, particularly dramatically in the aftermath of the 2019 to 2020 dimming event. The dust ejection that contributed to the Great Dimming was concentrated in the southern hemisphere of the star. One side dimmed more than the other, because one side expelled more material. The asymmetry was directly imaged, and the implication is consistent with what was seen in Antares. Neither of these stars is losing mass like a calm, spherically symmetric system. The causes of asymmetric outflow in red supergiants can be multiple. Rotation can introduce a preferred equatorial plane of mass loss. Large convective cells, giant bubbles of hot gas rising to the surface, can produce localized ejections. Binary interaction can impose a preferred geometry based on the orbital plane of the companion. In both the Betelgeuse and Antares systems, all three of these factors are plausibly operating simultaneously, which makes disentangling their contributions extraordinarily difficult. But the broader significance is what matters here. In stellar physics, symmetry is stability. The processes that maintain a star in equilibrium, the pressure from fusion supporting the weight of the outer layers, operate spherically. When the outflow geometry breaks down, when material is being preferentially ejected in certain directions while other regions remain more stable, it is a signal that the equilibrium itself is breaking down. The star is losing its structure before it loses its light. Both of these stars are showing that signal. Antares may be showing it with less visual drama, but the data suggests the underlying instability is equally real. Betelgeuse gets studied more because Betelgeuse is easier to study. That sentence sounds almost too simple to be important, but its consequences for how confident we are in the Betelgeuse over Antares ranking are genuinely significant. Consider the observational geometry. Betelgeuse sits at a relatively high galactic latitude, meaning when you look at Betelgeuse, you are looking somewhat away from the densely packed plane of the Milky Way. The field of view is comparatively clean. Background sources are manageable. Isolating the signal of the star itself from the noise of the surrounding environment is achievable with standard observational techniques. This is a practical advantage that translates directly into data quality and research volume. Antares sits near the galactic plane. When you look toward Antares, you are looking toward a region of sky packed with gas clouds, dust lanes, background star fields, and interfering emission sources. Every measurement you try to make of Antares competes with background contamination. Isolating the stellar signal cleanly requires more sophisticated data reduction, more careful modeling of the background contribution, and more observational time. This is not an insurmountable problem. It is a solved problem in principle, but it raises the cost and difficulty of every study. And in a research environment where funding is competitive and the low-hanging fruit of clean, unambiguous data is always attractive, that added difficulty steers effort away. Compound this with the cultural factor. Orion is one of the most globally recognized features of the night sky. Betelgeuse, as its brightest red star, enters the public imagination in a way that Antares, tucked in the seasonal, southern dominant arc of Scorpius, simply does not. Public interest drives science communication. Science communication drives public funding awareness. Public funding awareness influences grant priorities. The feedback loop is not direct, but it is real. More popular attention to Betelgeuse generates more popular science coverage, which generates more interest from early career researchers, which populates the citation base, which makes it easier for established researchers to write fundable proposals, which generates more studies. This is not a conspiracy. There is no coordinated suppression of Antares research. But structural bias does not require intent to operate. It requires only that the path of least resistance consistently points in one direction. And in this case, it consistently points toward Betelgeuse. The consequence is that we have achieved a level of confidence in our Betelgeuse characterization that may be slightly inflated relative to the actual data, while our Antares characterization remains comparatively thin. We may be overconfident about Betelgeuse precisely because we know it so well, and one missing event reinforces that illusion in a way that sounds like evidence but isn't. Someone at some point in this conversation is going to say, but Antares has not dimmed dramatically. There has been no great dimming for Antares. No viral headlines. No Twitter panic. No emergency repointing of the Very Large Telescope. If Antares were really as unstable as this comparison suggests, surely it would have done something dramatic by now. This argument sounds intuitive. It is also based on a misunderstanding of what the Great Dimming actually revealed. The dimming of Betelgeuse in 2019 was directly linked to its companion's orbital behavior, specifically a mass stripping event associated with a periodic encounter with the companion object. The companion plunges through the outer atmosphere, disturbs a large convective cell, triggers an ejection, and the resulting dust obscures part of the star. That is an episodic system producing an episodic signal. The drama was real, but it was real because of the particular geometry of how Betelgeuse's binary interaction works. It requires a close, periodic pass. Antares B does not do close, periodic passes. It is continuously embedded. The disruption is not delivered in concentrated shock events. It is spread continuously across the entire outer envelope. A continuous disturbance does not produce a sharp brightness drop. It produces something more like a slowly modulated, irregular variability pattern, which is, incidentally, exactly what Antares displays. Antares has what astronomers classify as semi-regular variability, with brightness changes of roughly 0.6 to 1.6 magnitude spread over irregular periods. That is not stability. That is a different kind of instability, one that does not generate dramatic events, precisely because the energy input is constant rather than pulsed. The absence of a great dimming for Antares is not evidence that Antares is less unstable. It is evidence that Antares is unstable in a different way. A star that is being continuously, persistently destabilized by an embedded companion is not going to broadcast its instability in the form of a single, dramatic, photogenic dimming event. It is going to show a slow, irregular, hard to dramatize fluctuation that does not attract headlines. Lack of headlines is not the same as lack of activity, and the real countdown, the one that matters, is not visible at the surface of either star. Here is the uncomfortable truth about everything we have discussed so far. None of it, not the mass loss rates, not the binary interaction, not the asymmetric outflow geometry, not the variability patterns, directly tells us what is happening inside the cores of these stars. And the core is where the countdown is actually running. A red supergiant in the late stages of its life moves through a sequence of nuclear burning phases, each one faster than the last. Hydrogen burns for millions of years. Helium for hundreds of thousands. Carbon for thousands. Neon for about a year. Oxygen for months. Silicon, the final stage before core collapse, for approximately 1 day. The star, from the outside, looks almost identical throughout most of these stages. The surface temperature might shift slightly. The variability behavior might change in subtle ways. But there is no surface signal that reliably and unambiguously says, this star is in its oxygen burning phase, or this star is in its silicon burning phase, or this star has approximately 400 days remaining before core collapse. The surface and the core are, in a meaningful physical sense, decoupled. The outer layers you observe with your telescope, the photosphere, the chromosphere, the envelope, respond to the thermal and pressure conditions of the outermost regions of the star. The core, buried under hundreds of solar masses of material, operates on its own schedule, processing fuel through fusion reactions that do not immediately telegraph their progress to the surface. By the time any surface signal changes significantly in response to late-stage core burning, the star may already be hours from collapse, rather than thousands of years. Think of it like this. You are watching smoke rising from a building. You can analyze the smoke, its color, its density, its direction, its chemical composition. You can learn an enormous amount about what is happening near the top of the building. But you cannot determine the state of the fire in the basement from smoke alone. The smoke tells you the fire exists. It does not tell you how close the fire is to the structural elements that matter most. That is the situation with both Betelgeuse and Antares. The surface signals are real, they are informative, and they narrow the probability range. But they do not resolve the countdown. And the uncertainty range, once you look at it honestly, is wider than almost any popular science article about these stars would have you believe. We keep coming back to mass loss because it keeps coming back to us. It is the best proxy indicator we have, and it is genuinely meaningful. But it requires more context than it usually gets. The rate at which a red supergiant loses mass is influenced by at least 3 major factors operating simultaneously, and they do not always point in the same direction. Rotation plays a role. A faster rotating star has a more oblate shape and experiences stronger centrifugal effects at the equator, which can couple with radiation pressure to drive stronger mass outflow at lower latitudes. The star's metallicity, the abundance of elements heavier than hydrogen and helium in its composition, affects how efficiently radiation pressure can push on the surrounding gas, because heavier elements absorb photons more readily than hydrogen and helium. And binary interaction, as we have already discussed at length, can drive mass loss through gravitational tidal effects and radiative processes independent of the star's internal evolutionary state entirely. What this means in practice is that observing a high mass loss rate tells you the mass is leaving fast, but it does not automatically tell you why. Antares could be losing mass at 10 times the rate of Betelgeuse, because it is genuinely further along in its evolutionary sequence, and the core instability is propagating outward in ways that drive the enhanced wind. Or Antares could be losing mass at that rate primarily because Antares B's continuous gravitational and radiative influence is actively driving material off the envelope, independent of where the core sits in its burning sequence. The observable is the same in both cases. The interpretation is not. This is not a reason to dismiss the mass loss comparison. It is a reason to hold it with appropriate uncertainty. In the multi-factor comparison between these two stars, mass loss is a meaningful data point. It does not become meaningless just because it has multiple possible causes. But it also cannot carry the full weight of a ranking on its own. You need to combine it with other indicators, account for the confounding influences, and then, honestly, acknowledge that the resulting picture is still incomplete. Antares might be further along. It might not be. The uncertainty range is not a footnote. It is the story. Let us talk honestly about the numbers for a moment, because this is where science communication about these stars most consistently fails the audience. When you read that Betelgeuse could go supernova at any time, or that it is expected to explode within the next 100,000 years, both of those statements can appear in reputable sources without either one being wrong. That is because the genuine scientific uncertainty range for when a star like Betelgeuse or Antares might reach core collapse runs from, essentially, right now to several 100,000 years in the future. Those are not two different estimates of the same thing. They reflect the actual probability distribution that the models produce when given the available data and the recognized limitations of our knowledge of the stellar interior. Astronomers are not being evasive when they give you this range. They are being accurate. The models are sophisticated. They are built on solid physics, and they have been tested against observations of stars in various evolutionary stages across many different systems. But they are fundamentally limited by the fact that they cannot directly observe the quantity they are trying to predict, the remaining fuel in the core. Every estimate flows through indirect inference chains, and those chains carry uncertainty at every link. The phrase "any day now" is, in a strictly statistical sense, not irresponsible when applied to either of these stars. A star in the late evolutionary stage of a red supergiant on a cosmic timescale is extraordinarily close to collapse. Whether extraordinarily close on a cosmic timescale translates to within a human lifetime, within recorded human history, or within the next million years, that is where the models lose their precision. And here's the thing that almost no popular treatment of this topic acknowledges clearly. Both Betelgeuse and Antares share this uncertainty equally. The confidence with which Betelgeuse is ranked as the more imminent candidate does not come from a comparison of their uncertainty ranges. Those ranges substantially overlap. It comes from the cultural and observational history of the subject, and from the asymmetric depth of analysis applied to the two stars. But history, it turns out, suggests something else is going on in our galaxy. In 1604, a supernova lit up the sky in the constellation Ophiuchus, visible in daylight, bright enough to be documented by observers across Asia and Europe, studied by Johannes Kepler and immortalized in his records. That event, known as Kepler's supernova, is the last naked-eye supernova observed in our galaxy. It has been over 400 years. 421 years to be precise. That gap is statistically unusual. The estimated rate of core collapse supernova in the Milky Way is roughly 2 to 3 events per century, based on multiple independent estimation methods including pulsar birth rates, supernova remnant catalogs, and observations of supernova rates in similar galaxies. If that rate is anywhere near correct, then between 3 and 6 supernovae should have occurred in our galaxy in the 4 centuries since Kepler's supernova. We did not observe them. Or rather, we observed the consequences of one of them, decades after the fact. Cassiopeia A is a supernova remnant sitting about 11,000 light-years from Earth. Based on the expansion rate of the remnant, the original explosion is estimated to have occurred around 1680, approximately 76 years after Kepler's supernova, well within the expected rate. But there are no credible historical records of anyone observing this event with the naked eye, despite its proximity on a galactic scale. The leading explanation is dust obscuration. The explosion occurred behind enough intervening material that the visible light was absorbed before it reached Earth, while the expanding shockwave and radio emissions that we detect today were not accessible to pre-technological observers. The universe is not cooperating with our observational limitations. Supernovae are happening in our galaxy on their expected schedule. We are simply not seeing all of them, because interstellar dust is an excellent barrier to visible light. This has an implication that cuts directly to the Betelgeuse-Antares comparison. Our 400-year gap without a visible galactic supernova does not mean we are statistically overdue. It may simply mean the recent events were obscured. But it also means our intuition that nothing big has happened lately is calibrated to our visual access to the galaxy, not to the galaxy's actual recent history. And when a nearby supernova does become visible, the first sign will not be optical at all. On the 23rd of February, 1987, a blue supergiant in the Large Magellanic Cloud, a satellite galaxy of the Milky Way at roughly 160,000 light-years away, collapsed and became Supernova 1987A. It was the closest observed supernova since Kepler's event, and it was visible to the naked eye from the southern hemisphere for months. Astronomers studied it in every wavelength accessible to the instruments of the era, but the most scientifically consequential signal from that explosion did not come from any telescope. At 3 underground neutrino detectors, the Kamiokande 2 facility in Japan, the Irvine, Michigan Brookhaven detector in the United States, and the Baksan Neutrino Observatory in the Soviet Union, a burst of 24 neutrinos was recorded over a span of approximately 13 seconds. Those detectors caught the signal approximately 3 hours before the visible light from the explosion reached Earth. 24 neutrinos from 160,000 light-years away. That is how sensitive modern neutrino physics has become at detecting these nearly massless, nearly interaction-free particles. And that was in 1987. Today, the global network of neutrino detectors is far larger, far more sensitive, and coordinated under a system called the Supernova Early Warning System, known as SNEWS. The Super Kamiokande detector in Japan alone would be expected to register thousands of neutrino events from a core collapse supernova at the distance of Betelgeuse or Antares, not 24, but thousands. The signal would be unmistakable, and it would arrive hours before the first photon of visible light reached Earth, because neutrinos escape the collapsing core essentially instantly, while visible light has to fight its way through the stellar envelope for several hours before breaking out into space. This means that the first announcement of a nearby galactic supernova will not come from an astronomer looking through an eyepiece. It will come from a particle physicist in an underground laboratory watching a detector that is measuring something invisible, arriving faster than light can carry the news. The SNEWS network will trigger automatically. Alerts will go out globally. Observatories will repoint. And then, hours later, a star that was invisible or unremarkable in the sky will begin to brighten at a rate no object in that position should be able to brighten. If it is Antares, if the first neutrino burst points to Scorpius, the sky as you know it will begin changing overnight. Allow yourself to imagine this for a moment, because the scale of it is genuinely difficult to process from within ordinary life. At peak brightness, a supernova from either Antares or Betelgeuse is expected to reach an apparent magnitude of somewhere around -12 to -13. The full moon sits at approximately -12.7. We are talking about an object in a fixed position in the sky, not moving, not diffuse, not spread across the horizon like the moon, but a point source, shining at roughly the brightness of a full moon. On a clear night, it would cast shadows. Your shadow at midnight, thrown by a single point of light in the sky. Antares sits in the southern sky for observers in the northern hemisphere, relatively low on the horizon during summer months. For observers closer to the equator or in the southern hemisphere, it sits higher and is visible for longer each night. When Antares reaches peak supernova brightness, it will be visible to every person on Earth with an unobstructed view of that region of sky. It will be visible during the day, a bright, colored point near or below the sun's position, distinct against the blue sky in ways that no other stellar object achieves outside of Venus under ideal conditions. At night, it will be the dominant visual feature of the sky for weeks. The transformation will not be instantaneous, but by cosmic standards, it will be breathtakingly fast. You will have perhaps a night or two where the star is noticeably brighter than it should be, where even a casual observer who knows nothing about astronomy will look up and say that something is wrong with the sky. Then the brightening will accelerate. Within a week, it will be unmistakable. Within 2 weeks, you will be explaining it to everyone you know. And for roughly 3 to 4 months, the sky will simply be different from any sky any living human has ever seen. The timeline of how it gets there is worth walking through carefully, because it is faster and stranger than most people realize. The beginning of a core collapse supernova is invisible. When the silicon burning phase ends and the iron core, which cannot release energy through fusion because iron sits at the minimum of nuclear binding energy, reaches its critical mass, the collapse begins. The inner core, several 100,000 kilometers across, collapses to a neutron star roughly 20 kilometers in diameter in less than 1 second. The infalling outer core rebounds off this newly formed neutron star and sends a shockwave outward through the rest of the stellar envelope. This entire sequence, from the onset of collapse to the formation of the neutron star, takes approximately 1 second. During this second, the core radiates roughly 3 times 10 to the 46th joules of energy in the form of neutrinos. That is more energy than the sun will emit in its entire 10 billion year lifetime, released in 1 second, and 99% of it leaves as neutrinos rather than light. Those neutrinos reach Earth, at Antares' distance, several hours after the collapse, because even traveling at the speed of light, they need roughly 550 years to get here, and the light travel delay has already been built in. The neutrino burst is the first detectable signal. It triggers the snooze network. It arrives hours before the visible light. The visible shockwave, the light that eventually makes Antares into a second moon, takes several hours to punch through the outer stellar envelope. This phase is called shock breakout, and it represents the moment when the energy of the explosion finally reaches the surface of the star and blows off the outer layers. A brief, intense ultraviolet flash occurs. Then, the optical brightening begins. Over the following days and weeks, the expanding shell of gas heats and brightens as it expands. The peak brightness is reached in the first few weeks. Then comes a plateau phase, roughly 100 days of sustained near-peak brightness, driven by the radioactive decay of nickel-56 into cobalt-56 into iron-56, releasing energy at a predictable rate. After the plateau, the light curve begins a slow, months-long decline as the expanding remnant cools and the radioactive heating fades. The closest modern template we have for this sequence is Supernova 1987A, which followed a similar pattern despite being a blue supergiant rather than a red one. The details would differ for Antares, but the broad architecture of the event, neutrinos, shock breakout, brightening, plateau, decay, would follow the same fundamental physics. And despite how intense all of that sounds, the thing most likely to surprise you about a supernova at this distance is what it will not do. The short version, you will be fine. The threshold for a supernova to pose a direct threat to Earth's biosphere through gamma-ray burst irradiation or enhanced cosmic ray flux severe enough to damage the ozone layer is generally estimated at somewhere below about 50 light-years. The exact distance depends on the orientation of the explosion relative to Earth and whether a gamma-ray burst, which is highly directional, is aimed in our direction. But both Betelgeuse at 640 light-years and Antares at 550 light-years are far outside that threshold by an order of magnitude. There is no plausible mechanism by which a supernova at either distance poses a physical threat to life on Earth. The neutrinos, for all their dramatic detection story, are functionally harmless at this distance. Neutrinos interact with matter so weakly that the flood of them passing through Earth during a nearby galactic supernova will result in, by some estimates, perhaps 1 or 2 interactions per person. In the most optimistic detection scenario, the trillions of solar neutrinos passing through your body every second right now are not affecting your biology, and the supernova neutrino burst, despite being far more intense for its brief duration, will not change that. The cosmic ray enhancement from the expanding supernova remnant happens over much longer timescales, centuries after the explosion. And at these distances, the flux increase reaching Earth would be far below the threshold required to produce measurable biological effects. The gamma-ray burst concern, which is the most serious risk from stellar explosions, does not apply to red supergiants, which are not the progenitors of long-duration gamma-ray bursts. Antares and Betelgeuse, if they explode, will produce core collapse supernovae associated with comparatively modest and isotropic high-energy emission, not the tightly collimated, catastrophically energetic jets of relativistic material that make some stellar deaths genuinely dangerous. What a supernova at Antares' distance will produce is an extraordinary visual event, a scientifically unprecedented opportunity to study a nearby supernova in every electromagnetic band and in neutrino physics simultaneously, a permanent alteration of the night sky as the remnant expands over decades into a new nebula, and a conversation humanity will still be having centuries from now. The danger is not physical. The danger, if you want to call it that, is existential in the philosophical sense. The knowledge that the universe contains this level of violence at this proximity, with this regularity, which brings us back to the real mystery. Here's the paradox sitting at the center of this whole investigation. Antares is closer. Antares loses mass faster. Antares hosts a companion that disrupts it continuously rather than periodically. Antares sits in an ionized, asymmetric, visibly disturbed envelope. By the metrics that most directly reflect observable instability in a red supergiant, Antares is at minimum Betelgeuse's equal, and by several measures its superior as a candidate. And yet the popular scientific consensus, the version of this story that appears in textbooks, in science documentaries, in magazine articles, in YouTube explainers, confidently presents Betelgeuse as the candidate and Antares as the runner-up. How did we arrive at that ranking, and how confident should we actually be in it? The honest answer involves several overlapping factors that have nothing to do with the data. The Great Dimming of 2019 made Betelgeuse a media event, and media events generate scientific focus, and scientific focus generates the literature base that becomes the foundation of consensus. Betelgeuse is observationally easier to study, so it has been studied more thoroughly, and thorough study tends to produce higher apparent confidence, even when that confidence reflects data quantity rather than data quality. And Betelgeuse lives in Orion, which is visible from most of the world for most of the year, and carries several thousand years of human cultural weight. None of this is evidence that Betelgeuse is the wrong candidate. It might well go first. The uncertainty ranges overlap. The core stage information we actually need to resolve the comparison is not available for either star, but the confidence with which Betelgeuse is promoted as the candidate, compared to the quiet way Antares is usually acknowledged and dismissed, reflects a process that has more to do with observational history and cultural attention than with a rigorous comparative analysis of both systems. Could something be systematically underexplored in the Antares data? Not through suppression or neglect. No researcher is hiding data. But through the structural bias of a field that has concentrated its most powerful tools on the object that is easier to see and more dramatic to discuss? That is a genuinely open question. And there is no evidence of wrongdoing because none is required. Bias does not need a villain. It just needs a path of least resistance, consistently taken, and that changes how we should think about the next supernova. Two red supergiants, Same evolutionary class. Similar ages, measured in the broad categories of stellar chronology. Both hosting binary companions that are actively disrupting their outer envelopes. Both showing asymmetric mass loss. Both sitting within a range where a supernova during the span of human civilization is not a remote possibility, but a genuine probability somewhere in the distribution. One is famous. One is not. The famous one had a dramatic dimming event in 2019 that became a global news story and triggered an unprecedented observational campaign. It has been imaged directly, mapped in radio, probed in ultraviolet, and modeled with progressively more sophisticated simulations. It has been the subject of more papers in the past decade than the other star has been the subject of in the past century. Its name is recognizable to people who cannot name the constellation it lives in. The other is 90 light-years closer. It is losing mass at roughly 10 times the rate. Its companion is a permanent resident rather than a periodic visitor, continuously ionizing the outer atmosphere rather than delivering episodic mechanical shocks. Its outflow is asymmetric in ways that infrared observation has recorded, but which have not been subjected to the same unified analytical scrutiny as its counterpart. And it sits there, in the summer sky, quietly fluctuating in brightness in the semi-regular pattern of a star that does not know it is supposed to be second. We did not misidentify the next supernova. We did something more interesting and more human than that. We chose which one to watch. We made that choice based on what was dramatic, what was accessible, what had accumulated enough prior attention to justify more attention. The choice was rational by the standards of how science actually works, filtered through funding cycles and publication incentives and the gravitational pull of existing literature. And it may turn out to be correct. Betelgeuse may well go first. But when you look at the actual data, the distances, the mass loss rates, the binary dynamics, the observational asymmetry, the honest position is not that Betelgeuse is the candidate. The honest position is that we have two candidates comparably late in their lives by any exterior measure we can apply, and the one we have decided is secondary has several metrics that argue against that ranking. The neutrino detectors are running right now in underground laboratories on multiple continents, waiting for a burst that will arrive before any light does. The snooze network is active. The alerts are configured. When the first signal comes, when the detectors register a flood of neutrinos from a collapsing stellar core, the direction it points will tell us which star we were actually watching, whether we knew it or not. And if that direction is Scorpius, if the star we ranked second turns out to have been collapsing quietly while we trained our best instruments on its more famous neighbor, then the sky will change. Not just the visible sky, not just the light arriving at our eyes on some clear summer night when Antares suddenly begins to outshine everything else. The conceptual sky, the one built out of assumptions about what we know, what we have measured, and which questions we have actually answered versus which ones we simply stopped asking. What happens when the star we ignored goes first? Maybe nothing changes for physics. The universe does not care about our rankings, but something changes for us. Because it would mean that the most important astronomical event in 400 years, the most spectacular celestial phenomenon any living human will ever witness, was standing in plain sight the entire time, losing its substance by the billion ton per year, glowing in the tail of the Scorpion, waiting.